In this video, I'll present how to recognize some types of unclean data. Well, what are some types of unclean data? Well, first we have missing data. This is where we have records in our data where we're missing individual data points or certain fields are missing. We have erroneous data, where we have errors in our data set. So these can be recorded measurement errors, invalid values, data entry errors, or string values where numeric values are expected. We have inconsistent data. So this is where, if we're pulling records from multiple systems, we risk one data set being out of sync with the other. So which data do we use if the data doesn't match? Well, it's one of the things we have to decide when we have unclean data that's inconsistent. We have non-standard data. So this refers to units of measurement, date formats, time zones. If we're pulling data in from different locales, we may need to standardize the data to a uniform format or measurement. And then finally, we have inaccurate data. Now, this is one we often have trouble correcting, but we can often detect it and remove it if necessary. If we get a value or measurement outside of a given range, or outside of an expected category, then we can declare it inaccurate. Well, let's start with missing data. So in this example of unclean data, we have some data points missing. These iris measurements have some points missing. There are a few ways we can deal with this. We can drop the records entirely. This is a common approach, but we can also fill in the missing data points, which we call imputation. And there are many techniques for doing so, such as zero filling or mean substitution. But we do have to be careful that we don't introduce bias or affect the representative values in the data. Now, what are some common sources of erroneous data? Well, a lot of times we have to look to see how the data was gathered. Does it come from sensor reading? Are there devices recording measurements? Are they server logs? Maybe manual data entry, some things typed in the keyboard. Quite often there can be mistyped values or mistyped variables. It could be even a sampling error. Are we randomly sampling? Do we get enough representative values? So erroneous data is also a source of unclean data that can be hard to clean or wrangle, but we can often detect it depending on the source of the error. Well, inconsistent data comes up if we have one system gets updated and another doesn't. So we have the same document in two different locations. If they get out of sync, they have different information. So we have to be careful which one we declare the reliable one or the current one. What about non-standard data? Well, along with weight measures like pounds, kilograms, or stone, or temperature measurements such as Fahrenheit, Celsius, and Kelvin, fields with dates come to us in many formats. If a source of data always has the same format, then we can consistently convert it to a standard format such as the ISO 8601 date-time representation. But if a single source of data has mixed or varying date-time formats, it could be a source of frustration and require us to be careful in our data conversion tasks. And finally, we have inaccurate data. This can be outdated data, imprecise data, or non-existent data. So we can often watch for extreme values, or we may need to reference external sources of data to verify the validity of the data. If we're dealing with location data, we may have a city or street address along with a zip or postal code. So we can identify inaccurate matches by looking up postal data references to make sure the zip code matches up with the given city or street. If we're dealing with outdated data, we can often just call the data and use more up-to-date values. And that concludes this presentation on types of unclean data. In this video, I'll present how to recognize criteria for ensuring data quality. What do we mean by data quality? Well, we're talking about the constraints on the data, the validity of the data, the consistency, and the data profile. Over the next few slides, I'll talk about these elements in terms of ensuring data quality. What do we mean by constraints on the data? Well, does the data conform to a minimum and maximum value? Does it fall within that particular range? Does it match a particular pattern? So quite often we have strings such as phone numbers, emails, and URLs that have to match a particular format. So the phone numbers, we might be expecting a country code, an area code, and a certain number of digits. The emails, well, we're looking for an @ symbol and a valid domain name. So those are the types of patterns we need to match for the constraints on these fields. What about the precision of the data? Are we recording to microseconds or milliseconds? So how precise is the data and how precise should it be? And then finally, do we allow missing or NA values in the data? Is it okay that some data points are missing? And how tolerant are we to missing data? When we talk about the validity of data, we talk about duplicates. So are there duplicates in our data set? If there are, this may skew or bias the results if there are too many duplicate records. The completeness of the data. Do we have enough data recorded? Are the samples we have representative of the data or the population? Are there too many missing values in the data? The recency of the data. Well, if we're carrying out some business intelligence or predictive analytics, we may only want to look at the past 2 years rather than the past 5 or 10 years. Our models may become invalid if we go back too far. And then finally, the uniformity. Is the data uniform in terms of its unit measurements and its date formats? Then we may need to consistency check our data. So this criteria for ensuring data quality is answering the question, do we have contradictory data? This comes up a lot if we're combining data or referencing data from multiple systems where records may exist in multiple places, or even from multiple points in time. So across our systems, do we have consistent data types? Do we have consistent set membership? And are the values consistent? Can we carry out particular joins across our various systems? And we have cross-validation. So this is to check the consistency of our models across different partitions, often subsets in time, where we ask, are the new models still consistent with the previous models? And finally, we have data profiling, or conducting the task of data profiling, where we get a high-level view of our data. So we carry out methods like gathering descriptive statistics like min, max, mean, frequency, etc. We carry out maintenance tasks, we integrate data into new systems or applications, we assess the constraints, the validity, and carry out consistency checks, as I mentioned in the previous slides. So we can make improvements to our data such as adding categories, descriptions, and tags to the data, and we can assess the performance of accessing the data and the performance when carrying out the necessary data science tasks, such as modeling or predictive analytics. And that concludes this presentation on data quality. In this video, I'll demonstrate how to fetch a JSON document over HTTP and load the data into a dplyr tibble. So we start out on line 1 with install.packages tidyverse. Now, Tidyverse is a package of packages that contains many tools for data wrangling, such as tidyr and dplyr, as well as the JSON Lite library, which we'll use in this video to load the JSON data into a dplyr table called a tibble. So on line 2, I bring in the entire package of packages, calling library tidyverse. So this will give us the entire tidyverse library. On line 4, I have a variable called weather_URL, and I assign that to the character string https://api.weather.gov/stations/kbhb/observations/latest. So this is the National Weather Service API, and I'm specifying the KBHB station, weather station, so this is the weather coming from Bar Harbor, Maine. So this API will return a document in JSON format. So on line 6, I have res is assigned to try catch, and the function we're going to execute inside of the try block is from JSON, so from, then capital JSON, and then I pass the weather_URL. So this will fetch from the endpoint specified by weather URL the JSON format. So it'll convert it to an R object and store it in res if it's successful. But since we're calling a remote API, we want to be aware that there can be an error. It can be a network error, there can be an API error, or some server error, or the API can change at some point and cause another error. So we need to be careful when we're actually making remote requests that we always try to catch an error if it occurs. And in this case, if there's an error, I have error equals function E, And in that block, I just do a stop and say failed to fetch JSON from URL. So depending on the program, you might want to handle errors differently, but in this case, I'm just going to stop the program at this point and not continue any execution. Now, supposing this is successful, on line 12, I do a glimpse of res. So a glimpse is a function that comes from the Tidyverse package, and it'll give us the structure of our res object. Now, I want to make sure that the API request returns the important response fields and that I'm getting a properly formatted response. So I'm checking on line 15 using an if statement. So I have if, then I have the exclamation mark for not. So I'm doing a not any of the vectors of the characters ID, geometry, and properties, %in% names of res. So if any of the names ID, geometry, and properties are not in the names of our response, then we're missing fields from the results. And we want to stop at that point because there's an error or we're not getting what we'd expected from the API endpoint. Otherwise, we just output OK in the else and continue on. Now in line 22, I'm going to extract the value I want from the endpoint. So this is the temperature in degrees Celsius. So on line 22, I have temp_c is assigned to res $properties, $temperature, $value. So it's the value of the temperature of the weather station, what it recorded at that point. And then I output temp_c. On line 26, I convert it to Fahrenheit. So I have temp_f is assigned to temp_c times 9 divided by 5 plus 32. And that will convert our temperature in Celsius to Fahrenheit. And I output that to make sure that the result is okay. Another important point from this data is the observation time. Well, when was this temperature recorded? So on line 30, I have observation_time is assigned to res $properties timestamp. And this timestamp is formatted in ISO 8601 datetime format at UTC time. So it's at time zone or time offset 0. And then I output the observation time result. And now I'm going to create a tibble, which is like a data frame, but particular to the dplyr library. So it gives us a few extra tools and a little bit more functionality, but it's basically an abstraction or a higher level version of our data frame. So I call this temperatures is assigned to tibble, and then I set the fields or the columns temp_c equal to their variable name. So temp_c is equal to temp_c, the variable. Temp_f is assigned to temp_f. And then the obs_dt or observation date time is equal to the observation_time. And then on line 38, I output temperatures, and 39, I do a glimpse of temperatures to see its structure. So now I'll run the code, and we can verify that the results match what I've just described. So I've selected Ctrl-Alt-R to run the code, run the entire source file, and in the console, we have the output. So I'll scroll up in the output, and I'll start at the beginning. So the first significant line of output is the glimpse of res. So it's a list of 5, and it gives us all of the details of the results of the endpoint. So it has a variable at context, ID, type, geometry, properties, all the things we check for later on. And has information like the wind direction, wind speed, wind gust. So it's very detailed information about the weather. Even though we're only looking at a single variable and the timestamp in this example, there's a lot that can be extracted from this. So I'll scroll down through until we get to the end of the glimpse, and we'll start at the next section. So the if statement, where it checks for important response fields, it does output OK as we'd expect. So it does contain the variables or the fields ID, geometry, and properties, so we have a well-formed response. When we extract the value, we get a current temperature of negative 8.9 degrees Celsius. So it's quite cold. And this temperature in Fahrenheit, when we've converted it, it's 15.98. The observation time, well, we can see it's in ISO 8601 format with 2019-02-01, so the 1st of February 2019, at 16:56:00, and then it has a plus and the time zone offset. In this case, it's an offset of 0, so it's in UTC time. And then our temperatures tibble that we've created gives us a 1x3 tibble, so it has temp_c, temp_f, and obs_dt, and the record contains the variables that we extracted. And if we glimpse the structure of it, it gives us one observation with 3 variables, temp_c, temp_f, and obs_dt, which gives us the types, the double, double, and character that represent these values. And that concludes this demonstration of downloading and reading JSON data. In this video, I'll demonstrate how to load multiple sheets from an Excel document. So on line 1 of this example, I have install.packages Tidyverse, but I have it commented out because I've already installed this package. If you don't have it installed, you can install it by uncommenting that line and running the code. Then on line 2, I bring in the read Excel library that comes from Tidyverse. So I have library, then read XL. So it's actually spelled out READ and the letters X and L. Then on line 4, I have XL_path is assigned to the string documents / names-is.xlsx. So that's the path of the file name that we're going to use in this example. Then on line 6, I have sheet_names is assigned to the function Excel_sheets, and I provide XL_path as its argument. So it's going to read the sheet names from this Excel document. And then on line 7, so we can see the contents, I do a glimpse of sheet_names. So now I'm going to do a Control-Enter on each line of code up until that point, so we can see the results of the glimpse of sheet names. And in the output, we have character strings. We have 2 of them in sheet names, people and eyes. So those are the 2 sheet names that we have in the document. So now on line 9, I can do people_names is assigned to read_Excel, and I pass the XL_path variable, and I also pass the argument sheet equals the string people. So this will read the contents of the people sheet. And then if I look at the contents of the people names, I see that it's a tibble, a 4x4 tibble, or a dplyr data frame with the columns ID, name, birth year, and education for 4 different people. And then on line 12, I do the same thing for the eyes sheet. So I have people_eyes is assigned to read_Excel, Excel path, and sheet equals eyes. In the contents of this, there's an ID, a name, and an eye color for 6 different people. Now on line 15, I do people_eyes. I use the dplyr pipe operator, so the % greater than %, and then I pipe that into count eye_color. So we'll count the occurrences of the eye colors. So this gives us the eye colors, blue, brown, and gray, and the number of each, the count of each. So there's 3 blue eyes, 2 brown eyes, and 1 of gray eyes in this data set. Now there's one more thing I'll mention, that when you're redoing a read Excel of an Excel document, if you don't specify a sheet, if I remove that code, say on line 9, so I have people names is assigned to read_Excel of Excel path, what this does when we don't specify the sheet, it just reads the first one. So this will actually give us the same result if I execute 9 and 10 again. But we have to be careful here because we never know the order of the sheets. If the sheets get changed, if another sheet gets added and say prepended to the document, it could read something else. So it's my recommendation that you should always specify a sheet unless you're certain that the document only contains a single sheet, then you can probably leave it off. But if it has multiple sheets, you always want to be explicit in case the order of the sheet changes. So I'll put the sheet equals people back in and then save. And that concludes this demonstration of loading multiple sheets from an Excel document. In this video, I'll demonstrate how to handle common errors encountered when reading CSV data. So I'm starting this video in a terminal window, and in this command line, I'm going to output using cat our example CSV file called cashew-example.csv. So I'll hit enter, and we can see the contents of this CSV file. So it starts with a header row that has a single space, then a comma. So the first column, the actual name of the column, is a single space with the values 1 to 5. Then we have country, comma, and then in double quotes, we have cashew production 2016, and in parentheses, metric tons. And then another comma, and then percent, the actual percent symbol of world total, comma, percent change from 2015. So there are some varying things going on here. There's a column with a space. There's a column name with just a single name. There's one that's enclosed in double quotes. There's some with special characters like percent symbols. The fourth record for Côte d'Ivoire actually has a single quote used as an apostrophe within the string. So if we're not careful how we read it, if we're using the single quotes as delimiters for the columns or to extract the actual country names, we may run into problems. Then we have the production amounts. So these are numbers. Then we have percent of world total and percent change from 2015. So the percent of world total and the percent change have a number followed by a percent symbol. Some of them are negative, like the change can be negative. Some values are missing, like the Nigeria result doesn't have the change from 2015. That's missing, so there's just a trailing comma. India, the actual change amounts don't have the percent symbol, and there's a trailing comma at the end, so it almost indicates that there's 6 columns, but there's not. So this is an errant comma at the end. So that's something you might run into. Côte d'Ivoire doesn't have the actual percent of world total. It just has the percent symbol by itself. And the Philippines result, the change from 2015, there's a space between the negative value and the actual number. So there's a hyphen or a dash, and then a space, then the number 4.1%. Now I'm going to tab over to RStudio, and I have some example code that's going to read this file in and parse it. And we're going to wrangle the data a bit. So we're going to handle the errors, and we're going to clean it up in this example. So on line 1, I bring in Tidyverse. So even though there's a built-in read.csv function contained in R, I prefer to use the more robust one provided in the Tidyverse package. So there's a function called read_CSV from the read_r package inside of Tidyverse. So on line 3, I have cashew_producers is assigned to read_CSV, and then I open document/cashew-example.csv. Same one that we did a cat of in the terminal window. Now, the nice thing about this, some of the errors it encounters, the ones that it's not sure about, it gives us warnings for. So it gives us one parsing failure. So on row 3, 5 columns, but there's actually 6 columns in this row because of that trailing comma. So we have to be careful at how this parsed it. And on line 4, I do a glimpse of cashew_producers just to see what's going on. So it does give me 5 observations and 5 variables. So that empty 6th one that it ran into or it wasn't sure about, it gave us a warning for on line 3, it just ignored it and dropped it. So that was probably a good choice. And then if we look at the contents of our cashew_producers, we can see all the values, how they were read by read_CSV. Now, the important thing here that we'd like to look at is what we need to clean up and what might cause us problems. Well, the data types, the first column with just the empty space, just has the rank of each column. So it's a double with 1, 2, 3, 4, 5. But that's the same as the row numbers, so we could probably drop the first column. In the country column, I'd like to get rid of the leading and trailing single quotes, but I have to make sure I keep the single quote that's in the Côte d'Ivoire entry that's used as an apostrophe. So we have to keep the apostrophe, but drop the leading and trailing quotes. The percent of world total, well, this was read in as a CHR or character string. So what I'd like to do is convert this to a number. So we'll need to remove the percent characters and convert it to a numeric value. And the same with the percent change. So on line 7, I create a variable called tbl_cashew to contain the cleaned results from our cashew producers. So I assign that to cashew_producers. Then I use the dplyr pipe library, so % greater than %. And now I'm going to compose a whole bunch of functions that will clean up our data set. The first one on line 8 is a select with -1. So this says drop the first column and keep all the rest. So we're dropping the rank column, but we're keeping everything else. Then I pipe that into a select where I select country equals 1, production equals 2, %_total equals 3, and %_change equals 4. So that's renaming each of the columns by their numeric index so we can have simpler names that are more easily to access programmatically. Then on line 11, I have a mutate. So this mutate function is going to change the contents of our table, of our tibble. So I have country equals the Csv function. So this takes the pattern I'd like to replace and what I'd like to replace it. So I'm doing a substitution. So in this case, I'm specifying a regular expression. And so in parentheses, I have a caret and a single quote. So if the string starts with a single character, so if we encounter a single quote leading the string, or so the pipe character in parentheses, a single quote $. So this is saying if there's a single quote at the beginning or the end, replace it with nothing. So discard it. And we're doing a gsub on the country column. The %_total, well, I'm doing an as.numeric, but before I do that, I need to wrap this around a gsub of the % character. So I want to drop the % character from the %total column. So I'm replacing it with nothing. So I'm discarding it. And then the %change or %_change, I also do an as.numeric. But the gsub here is a little bit more precise. I mean, I could have used the same one inside of the %total, but I wanted to demonstrate something else. So I'm using a regular expression. So if the character is not, so the caret 0 to 9 dot dash or minus. So I only want to keep the numbers 0 to 9 dot and dash. So this is inside of square brackets. I replace everything else with the empty character. So if it's a space or a % symbol or something else, it's going to discard those in the column and do an as numeric with the result. So I'll execute line 7 to create tbl_cashew. So it was created successfully. And now when I execute line 15 to show the contents of it, we get very nicely formatted 4 columns and 5 entries. We've removed the single quotes. We have our columns converted to numeric types or DBLs for double. And the %total for Côte d'Ivoire on line 4 is converted to NA instead of the single % symbol that was there. And we ended up with this clean table of data that we can work with. And that concludes this demonstration of reading dirty CSV files. In this video, I'll demonstrate how to read data from a relational database using a SQL query. In this example, we're using the rMariaDB package. This isn't just for MariaDB, it's also for MySQL, and it's interchangeable in both, since MariaDB is a drop-in replacement for MySQL. Though there's still a package in R called rMySQLDB, you should still use this rMariaDB package even if you are using MySQL. It is an updated database interface, and it's the current one. So in my case, I'm using Ubuntu, so before I install the rMariaDB package, I had to run sudo apt install libmariadb-client-lgpl-dev. So that gives me the dev library so that I can compile the rMariaDB package. And then on line 2 of my example code, I have install.packages rMariaDB. But I've commented it out because I've already run it prior to recording this video. Now on line 4, I bring in the database interface, library DBI. And now I can make a connection to MariaDB. Now I'm connecting to a group that's specified in my dot file, my.cnf. Now this has the information like the database name, the username, and the password to connect to the database. because I don't want to type that. I don't want my password appearing in my code. I want to keep that separate. And that's a best practice that we use nowadays for security reasons. So on line 6, I have a con variable that I assign to dbConnect, and now I specify r MariaDB :MariaDB and then parentheses. So this says to the database interface that we're connecting to MariaDB. And now I specify the groups as specified in my my.cnf file, which is called mydb-group. So now I'll test the connection and see if I can connect to it. And now we're connected to our MariaDB database. Now on line 9, I call dblistTables using the connection to see what tables are in my database. And there's a single table in this database called person. So on line 11, I'm going to do an insert. So I have insert_result is assigned to dbSendQuery, and SendQuery takes a connection and then a string with the SQL statement. In this case, the SQL statement is insert into person values null, Jane, and 2002. So there's 3 fields in this table: the ID field, which is an auto increment, so we can specify null, the name field, a person's name, and their birth year. So if we can change this to something, I've inserted a few already, and I'm going to call this one Alex, and Alex was born in 2005. So I'll execute this query on line 11, and then I'll check the db has completed function of our result, of our insert result, to see if it has completed. And then it says true. So the result is completed and we've inserted this in the database. So now let's do a select, and we're going to select all the records from person, and we can see what's there before this video, and we can see the person that we just inserted called Alex. So on line 14, I have result is assigned to dbSendQuery with con and then the string select star from person. So we're going to execute our query now. And now we'll look at the result variable. So the result doesn't actually have the results. It just shows us some information about the result object. If we want to fetch our results, we need to call dbFetch. So on line 16, I have dbFetch. I specify result and the number of rows I'd like to fetch. If I want to fetch all rows, I say n equals -1. Now I've executed that, and in the console, I get the results. I have 1, Steve, and the birth year 1897. Person ID 2 is Jill with 1977. 3, Bill, born in 1947. And our last one, 4, Alex, born in 2005. And now I'll check the has completed on this result by calling db has completed, which returns true. And then when I'm dealing with a result set or a MariaDB result, a good practice is to call dbClearResult after I'm finished processing the results. So I call that on line 19. And then when I'm finished with the database, I call dbDisconnect on our connection object, and that disconnects from our database. And that concludes this demonstration of querying relational databases in R. In this video, I'll demonstrate how to combine 2 related datasets using a join operation. So the first 6 lines of code in this example were seen in the video titled Excel Sheets. So I'll execute those now. So I've read 2 sheets from an Excel file with data compatible for a join. So we'd like to perform a join on the respective ID columns. So the contents of people_names are this tibble with the ID column, name, birth year, and education. The people eyes column, or the people eyes data, has ID, name, and eye color. So I'd like to combine these 2 data sets with a join. So on line 11, I do a left join. So this will join based on the people names first and the people eyes second. So it will contain all of the records from people_names and then the records from people eyes where they exist. And if they're not present, it puts NA in its place. So I'll execute the left join on people names and people eyes by ID. And that gives us a new table with ID name.x. So in the case where there's a collision of names or a collision of columns, it actually appends a .x and a .y respectively so that it can differentiate the columns in the new table that was created based on the join. So it has name.x, birth_year, education, name.y, and I_color. So it's combined them. So the result contains 4 records, the records that were in the people names sheet, but people eyes had 6 records. So those records that weren't in people names after the join, they were dropped because they didn't exist in the left-hand column, the people names column. Now, if we do a right join, so on line 12, I have right_join, people_names, people_eyes, by ID. So in this case, it will take everything from the right side, so from people eyes, which is to the right of people names, and then it will try to match it up with the ID in people names. Now, since there are more records in people eyes, there's going to be a few that it has to fill in with NA values. So let's execute the right join. And in the results, we get the 6 records that were in people eyes. But then where the IDs don't exist in people names, it fills in those values with NAs. Otherwise, it behaves similarly. And that concludes this demonstration of combining 2 related datasets using a join operation. In this video, I'll demonstrate how to reshape tabular data by spreading values from rows to columns. So in this example, on line 1, I have install.packages Tidyverse, but it's commented out because I already have it installed, so I don't need to run this line of code again. But on line 2, I call library of Tidyverse to bring in those packages. So what I get from Tidyverse, the first thing I get is the read CSV function. So the data for this example is in a file under documents/name-properties.csv. So on line 4, I have people_data is assigned to read_CSV with the character string documents/name-properties.csv passed to it. So now if I run the first few lines of code, I get this people data dataset loaded into my workspace. Now on line 5, I output the contents of people data so we can see what we're working with. So I'll scroll up in the console to the top of the dataset. So we have a tibble, this data frame of 20 by 3. So we have 3 columns and 20 entries. And those entries are an ID, a property, and a value. And if we inspect the properties, so we have the ID repeated. So there's 1, 1, 1, 1. So the ID is repeated 4 times for the property name, birth year, education, and salary. And then the values, we have the name, Steve, birth year, 1897, education, some categorical number, 6, salary, 50,000, and then it's repeated for IDs 2, 3, 4, and 5. So each ID has 4 entries. But what we'd like to do is reshape this. So instead of having these properties like name, birth year, education, and salary, we'd like to have those as actual columns. And then each row will be a single ID with its corresponding values according to these properties. So to do this, we use a spread function. Now, one thing I have in my code on line 6 is just a count of the IDs. So we can see that we have the IDs 1, 2, 3, 4, and 5. But then there's 4 of each. So we're working with 4 columns in the end because there's 4 entries we'd like to convert into, or we'd like to spread from this column format into a wider row format. So on line 8, I take people data again. I use the dplyr pipe operator, so % greater than %, and I pipe it into the spread function. And here I specify the columns I'd like to include in the spreading of the values. So first we have property, and then we have value. So if we execute line 8, so what gets printed to the console is the result of this spread. So we have the IDs, but here we just have 5 rows. So the IDs 1, 2, 3, 4, and 5. And then the columns now become birth year, education, name, and salary. And the property and values we had before are gone because we use those in creating this spread version of the table. And that concludes this demonstration of spreading values from rows to columns. Well, in this example code on line 1, I have install.packages tidyverse. Well, I have it commented out because the package is already installed. So I can just proceed to line 2 and call library of tidyverse. So I'll execute that now, and we can load tidyverse into our workspace. Now for this example, I'm working on the iris dataset. So this is a built-in dataset in R, and I'm going to call glimpse on iris. So on line 4, I execute glimpse of iris so we can see what we're working with. So it tells us there's 150 observations, so there's 150 rows in this dataset across 5 variables. And those variables are the measurements of various species of iris. So we have sepal.length, sepal.width, petal.length, petal.width, and the species. But this glimpse, this small summary, doesn't give us too much information. It shows us a few of the measurements, and the species is a factor, but in this glimpse, we only see one species, the setosa. Well, if we'd like to know more about what species we're working with, we can count them. So on line 5, I pipe iris into count of species. So when I execute that, I see in the output, we have 3 species, setosa, versicolor, and virginica, and there's 50 measurements or 50 observations of each. But this doesn't give us a sense of how they compare. Well, for that, we need a more apt summary. Now on line 6, I pipe iris into sample n with 12. So this will take a random sample of 12 of the records from this data set. And if we inspect this in the console, we see that we have some versicolor, some setosa, versicolor, virginica, but we have more setosas than we do have the other species. If we look at the measurements, we might be able to, eyeball it and get some sense of what's going on. But it's not really clear. It's hard to form a mental picture or a mental model based on just looking at a sample of records. Now, a more appropriate way of doing it is using summary functions. So this will give us a better sense of how these species compare, at least at a high level overview. So on line 8, I take the iris dataset, I pipe that into the group by function provided by the Tidyverse package inside of its dplyr library. So we have group underscore by, and I specify species, and then I pipe that into the summarize function. And here I have average equals the mean of petal.length. So I'm going to compare the petal lengths of each of the species, and we're going to look at their averages and their min and max values. So I start with summarize average equals mean of petal.length, the min equals min of petal.length, and max equals max of petal.length. So our column names will be average, min, and max created by this summary. So if I execute this code, in the results we have our 3 species, setosa, versicolor, and virginica. The averages 1.46, 4.26, and 5.55. The min for the setosa is 1, and its max is 1.9. So that's the petal length. It's between 1 and 1.9 centimeters. The versicolor is between 3 and 5.1 centimeters. And the virginicas are between 4.5 and 6.9 centimeters. Now we can see from this, we get a sense that the setosas are a much smaller species of iris. The versicolors sit somewhere in the middle, but there is some overlap with the virginicas. So if we wanted to classify these species based on the petal lengths, there is some overlap where our classification algorithm might run into problems. So if we look at the max value for versicolor, we have 5.1, but the min value for virginica is 4.5. So there is a bit of overlap here. So these are some things that stand out to us when we look at these summary functions. And that concludes this demonstration of summarizing data using dplyr in the Tidyverse package. In this video, I'll demonstrate how to use mean imputation to replace missing values or NA values in a dataset. So at the beginning of this code, in the first line, I have install.packages tidyverse. But it's commented out because I don't need to run it again because I already have it installed. So we'll proceed on line 2 where I call library of tidyverse so we can bring in the relevant libraries to this video. Now in line 4, I create a dataset, a data frame called iris_missing, and I assign that to the function tbl_df. So this converts from an R data frame to a dplyr tibble that we have from the Tidyverse library. And then I'm using the from JSON function to load this JSON dataset. So the dataset is in document/iris_missing.json. So in this version of the iris dataset, we're working with data that's missing some petal width measurements, a few for each species. So I'll execute line 4, and we'll display the data in iris missing at this point. So what's happening in this case is where we have a missing value, we get an empty string. So the consequence of this is that the petal width column is seen as a character string type, rather than a numeric type. And what we want is these missing values not to be empty values, but NA values. So we can use the NA helper functions provided by R. So on line 6, I'm going to modify iris_missing. So I'm going to assign that to iris_missing piped into the mutate function, where I set the petal_width equal to as.numeric of petal width. So this will convert the column to actual numeric values, and anywhere it sees an empty string, it will convert them to NA. And another thing I'd like to do is clean up the species column. So the species column is also seen as a string column, but I want it to be a factor column. So I set species equal to as.factor of species. So when I execute this code, it will make those modifications. And on line 10, I'm going to examine the data set, but I'm going to filter it. So I take iris_missing and I pipe that into the filter function. And I want to return the rows where is.na of the petal width is true. So when I execute that, I get all of the values where the petal width is set to NA. Now you'll notice that the types have changed. The petal width column in the output is showing as DBL or double, so it's a numeric value, but the entries are NA. So we'd like to take care of those, and this is where we're going to use our imputation method. And the species is now seen as a factor. So that cleans up things a little bit. So now we can look to replace the missing values. Now, one way to replace the NA values is to zero them out, though it's probably not the ideal method of replacing the missing values in this case. So if we're looking at summary statistics of the petal widths, zero values will cause some unneeded skew. So the averages will all skew downward if there are some zero values in there. So that's not a good way to replace values, at least not in this data set. For this example, a better way to replace the missing values is with the average values. But we don't want to average the petal width for the entire data set to replace the NAs. We'll need to average based on the particular species that we're working with. So in statistics, we call this imputation. So we're imputing the values by a method called mean substitution. So we're going to substitute the values with a mean value or average value. And on line 13 is where I start this computation. So I'm going to call the resulting data set iris_tbl, and I assign that to iris_missing piped into the group by function, so group by species, and that's piped into the mutate function. So I do a mutate where I set petal_width equal to the if-else function where I test is.na of petal width. So I only want to replace the NA values. So if it's NA, I replace it with the mean of the petal_width, and then I do an na.rm equals true. So I'm going to group by the species, take the mean or the average of the petal width, but I want to exclude the NA values because that'll cause some problems in the mean computation. Otherwise, if it's not NA, I just leave the petal width as is. So I'll execute this code, and we can examine the resulting data set. So I'll examine iris_tbl, and one of the values shows up quite early on. So where we had an empty string originally, then an NA value, once we did the replacement, we now have 0.245. So that's the average petal width, or the mean petal width, for the Setosa species. Another thing we can check is use the NA function on our iris dataset on iris_tbl. And if this returns true, that means we didn't get all the NA values, but in this case it returns false, so we have replaced them all. And that concludes this demonstration of imputing data. I'll demonstrate how to use a regular expression to extract data into a new column. So on line 1 of this example code, I bring in the library Tidyverse. The example data we're working with is a syslog file from a web server that logs HTTP requests to the syslog, which has subsequently been converted to a CSV file. So we'll read this CSV file and convert it to a dplyr tibble, and then extract only the user agent field. That's the only one we're concerned with for this example. So on line 3, I have raw underscore user underscore agents is assigned to the tbl underscore df function of the read underscore CSV function of the string documents slash syslog hyphen http.csv. So we're reading this file into a CSV, but then we're going to pipe it using the dplyr pipe operator percent greater than percent into the select function where we select only the user underscore agent field. So I'll execute that line, and then I'm going to call the head of raw user agents, and it'll give me the first few records, the first 6 records of this new tibble that we've created. So these user agents have some information about the browser that connected to the web server and that request was logged. So we have Mozilla /5.0, we have the desktop x11, Ubuntu, Linux x86 underscore 64, RV64, Gecko, which is the rendering engine, and then Firefox at the end /64, and it trails off. But what we're going to extract is actually the last item in this user agent. So where we have Firefox /64, so it's cut off a little bit, but the last word, so from the last space to the end of the user agent, we get the browser name and the version number. And I'd like to extract this information. So on line 7, I create a new tibble called user underscore agents underscore TBL, and I assign that to the raw user agents piped into the mutate function. And the mutate's going to create a new field called browser underscore info and set that equal to the string extract function, so str underscore extract of the user agent field, and then I specify a regular expression string. So I have inside of square brackets, I have the not or the caret, double \s for a space. So we're looking at not space plus $sign. So it's going to take everything up until the end of the string, so up until the $sign, but not including the space. So everything after the last space will be included in this extraction. So we create this browser info column using mutate, but then we pipe that result into the separate function. So the separate function comes from the tidyr library inside of Tidyverse, and we specify the browser info field, so the new field we've created, then a vector of the new columns that we'd like to create using separate. So we're taking one column and we're separating it into 2, the browser and the version. And the separator for this, we specify sep equals the string with the /. So I'll execute this entire command, and now we'll look at the results. So we have on line 11, user agents, tibble, $browser. So that gives us all of the browsers or all of the software used to make the web requests that were logged. So we have in the output many requests from the Firefox web browser, but we also have the curl utility, the curl command line utility making web requests, the Safari web browser, and the Edge web browser. And if we output the versions, so we have a number of versions here, 64.0, 7.74, 605.1.15, and one at the end, 17.17134. So we've extracted all of this information using a regular expression and some of the data wrangling tools from the Tidyverse package. And that concludes this demonstration of extracting matches. In this exercise, you'll load data from either a JSON, Excel, or CSV document, then handle missing data if necessary, or carry out any other data wrangling tasks you need to. Then extract some data into a new column, either based on some subset or some computation of a previous column. Then apply a summary function or aggregation on the data. Now you can pause the video and perform the exercise, and when you've completed it, come back to the video to see what I did. Now here's how I carried out the exercise. So on line 1 of my example, I bring in the library Tidyverse. Now the file I'm going to use is an Excel file. So I create a variable called xl_path, and I assign that to document/coldest_places.xlsx. So I create the variable, and then I call Excel Sheets on the Excel path, and I store that in sheet names. I'll do a glimpse of this on line 6 to see what the sheet names are. And in this example, there's only a single sheet called coldest_places. So on line 8, I create a variable called coldest_places, and I assign that to read Excel of Excel path. Now I'm not specifying a sheet because there's only one. And now let's have a look at what the coldest places contain. So this is a tibble 5x3, so there are 5 records and 3 columns. So the first column is a rank, so it has the numbers 1 to 5. The second one is a name, where it has 5 place names, and then their average temperature. So it's sorted by the coldest to the least cold of the 5 coldest places on Earth. Now, the average temperature in this case is in degrees Celsius. So we have negative 56.7 degrees C. So I'd like to do some things with this data set. Well, we don't have missing values, but I have an extra column at the front here I want to get rid of. I don't need the rank. I'm just going to use the actual row labels, the row numbers 1 to 5. And we're going to discard the first column. So on line 11, I have coldest places, and I assign that to coldest places, but I pipe that into some various functions. The first one is a select of -1. So this will drop the first column and leave us with everything else. And then on line 13, I do a select where I set place equal to 1 and temp_c equal to 2. So it will rename the columns to place and temp_c. Then on line 14, I do a mutate. So I'm going to take the temp_c column, and I'm going to convert that to numeric. So I call as.numeric. Because if you notice in the output, the temperature column is a character string column. So what I'm going to do is do as.numeric of a gsub, where I'm going to substitute where I have anything that's not a number, a decimal, or a negative symbol. I'm going to remove it from the string. So I'm going to replace it with the empty string. So we'll get rid of the degree symbol and the C. And then we're performing this on temp C. So we're overwriting the existing temp C, so we're mutating it. And then after that's performed, I pipe that into another mutate where we create our additional column. So we're extracting the temperature in C and converting it to temperature in Fahrenheit. So I mutate temp_f, so the new column is temp_f, and I assign that to temp_c times 9 divided by 5 plus 32, and that will convert it to Fahrenheit. So let's execute this code. And at this point, I can inspect the coldest places and see what the result is. So I have a cleaned up data set with the place, the temp C with no degree C in it, so we have numeric values, and then the temp_f, so the temperature in Fahrenheit. And now I'm going to carry out a summary function. So I take coldest places and I pipe that into summarize, where I set coldest equal the min of temp C and the least cold. I wouldn't call it the warmest, so I called it least cold. And I set that to the max of temp C. Now the min value is going to be the coldest value, and the maximum value, the least negative, is going to be the least cold. So we'll execute this summary, and we can see that the coldest is negative 56.7, and the least cold is negative 24.2. And that concludes this exercise on wrangling data in R.